In the name of Almighty God, I'm Mahsa Sankoshi, and today I want to talk about three-dimensional electrochemical and thermal analysis of prismatic lithium battery. Prismatic lithium batteries are rectangular, hard-case aluminum or steel cells designed for high space utilization, greater than 90% and efficient, compact stacking in EVS energy storage systems and industrial applications. They offer high capacities, about 10 to 300 long cycle life and superior structural thermal stability compared to cylindrical cells. And what are the key features and advantages? The first one is design. Feature a rigid rectangular shell allowing for higher energy density per volume and easier, more efficient module integration. The next one is capacity. They typically offer higher capacity per cell than cylindrical counterparts, requiring fewer cells, connections, and wiring to build large battery packs. The next one is applications. Ideal for electric vehicles, solar energy storage, and industrial backup systems due to their durability. The next one is safety and life generally offer improved safety, and in the case of lithium iron chemistry, a long lifespan of 3,000 to 7,000 cycles. And what are the disadvantages? The first disadvantage is manufacturing and cost, because manufacturing is more complex, resulting in higher initial costs compared to cylindrical cells. The next disadvantage is thermal management. While structurally robust, they may not perform as efficiently in extreme temperatures, requiring careful thermal management. Commonly available in LiFePO4 and lithium-ion chemistries, they are a dominant choice for stationary energy storage and large electric vehicle battery packs. Lithium-ion battery. A lithium-ion battery or Li-ion battery is a type of rechargeable battery that uses the reversible intercalation of Li plus ions into electronically conducting solids to store energy. Lithium-ion batteries are characterized by higher specific energy, energy density, and energy efficiency, and a longer cycle life and calendar life than other types of rechargeable batteries. Also, Northvolt sees a dramatic improvement in lithium-ion battery properties after their market introduction in 1991. Over the following 30 years, their volumetric energy density increased threefold while their cost dropped tenfold. In late 2024, global demand passed 1 terawatt hour per year, while production capacity was more than twice that. The invention and commercialization of lithium ion batteries has had a large impact on technology, as recognized by the 2019 Nobel Prize in Chemistry. Lithium ion batteries have enabled portable consumer electronics, laptop computers, cellular phones, and electric cars. Lithium ion batteries also see significant use for grid scale energy storage as well as military and aerospace applications. Stanley Whittingham conceived intercalation electrodes in the 1970s and created the first rechargeable lithium-ion battery based on a titanium disulfide cathode and a lithium aluminum anode, although it suffered from safety problems and was never commercialized. John Goodenough expanded on this work in 1980 by using lithium cobalt oxide as a cathode. The first prototype of the modern lithium-ion battery, which uses a carbonaceous anode rather than lithium metal, was developed by Akira Yoshino in 1985 and commercialized by Sony and uh, Kosei team led by Nishi in 1991. Whittingham, Goodenough, and Yoshino were awarded the 2019 Nobel Prize in Chemistry for their contributions to the development of the lithium-ion batteries. Lithium-ion batteries can be a fire or explosion hazard as they contain flammable electrolytes. Progress has been made in the development and manufacturing of safer lithium-ion batteries. Lithium-ion solid-state batteries are being developed to eliminate the flammable electrolyte. Recycled batteries can create toxic waste, including from toxic metals, and are a fire risk. Lithium and other minerals can have significant issues in mining, with lithium being water intensive in often arid regions, and other minerals used in some lithium ion chemistry potentially being conflict minerals such as cobalt. Environmental issues have encouraged some researchers to improve mineral efficiency and find alternatives such as lithium-ion phosphate lithium-ion chemistries or non-lithium based battery chemistries such as sodium-ion and iron-air batteries. Lithium-ion batteries can be considered as a generic term involving at least 12 different chemistries. See list of battery types. Lithium-ion cells can be manufactured to optimize energy density or power density. Handheld electronics mostly use lithium polymer batteries with a polymer gel as an electrolyte. A lithium cobalt oxide cathode material and a graphite anode, which together offer high energy density. Lithium iron phosphate and lithium manganese oxide, and the other composition, and lithium nickel manganese cobalt oxide may offer longer life and a higher discharge rate. NMC and its derivatives are widely used in the electrification of transport, one of the main technologies combined with renewable energy for reducing greenhouse gas emissions from vehicles. History of the lithium-ion battery. Research on rechargeable lithium-ion batteries dates to the 1960s. One of the earliest examples is a CUF-2Li battery developed by NASA in 1965. The breakthrough that produced the earliest form of the modern lithium-ion battery was made by British chemist Stanley Whittingham in 1974, who first used titanium disulfide (TiS2) as a cathode material, which has a layer structure that can take in lithium ions without significant changes to its crystal structure. Exxon tried to commercialize this battery in the late 1970s, but found the synthesis expensive and complex, as TiS2 is sensitive to moisture and releases toxic hydrogen sulfide gas on contact with water. More prohibitively, the batteries were also prone to spontaneously catch fire due to the presence of metallic lithium in the cells. For these and other reasons, Exxon discontinued the development of Whittingham's lithium titanium disulfide battery in 1980, working in separate groups. Ned Gottschall and his colleagues, and shortly thereafter Koichi and Goodenough, after testing a range of alternative materials, replaced TiS2 with lithium cobalt oxide, which has a similar layer structure but offers a higher voltage and is much more stable in air. This material would later be used in first commercial lithium-ion battery, although it didn't, and its own resolve the persistent issue of flammability. These early attempts to develop rechargeable lithium-ion batteries used lithium metal anodes, which were ultimately abandoned due to safety concerns, as lithium metal is unstable and prone to dendrite formation, which can cause short-circuiting and the eventual solution was to use an intercalation anode, similar to that used for the cathode, which prevents the formation of lithium metal during battery charging. The first to demonstrate lithium-ion reversible intercalation into graphite anodes was during Otto Besenhard in 1974. Besenhard used organic solvents such as carbonates. However, these solvents decomposed rapidly, providing short battery cycle life. Later in 1980, Richard Yazami used a solid organic electrolytic polyethylene oxide, which was more stable. In 1985, Yoshino at Kasi Corporation discovered that petroleum coke, a less graphitized form of carbon, can reversibly intercalate lithium-ion at a low potential of about zero point 0.5 volt relative to lithium positive and lithium without structural degradation. Its structural stability originates from its amorphous carbon regions, which serve as covalent joints to pin the layers together, although it has a lower capacity compared to graphite, about lithium zero point 0.5 C6, 186 mAh, and it became the first commercial intercalation anode for lithium-ion batteries owing to its cycling stability. In 1987, Yoshino patented what would become the first commercial lithium-ion battery using this anode. He used Goodenoug's previously reported LiCO2 as the cathode and a carbonate ester-based electrolyte. The battery was assembled in discharge state, which made it safer and cheaper to manufacture. In 1991, using Yoshino's design, Sony began producing and selling the world's first rechargeable lithium-ion batteries. The following year, a joint venture between the Toshiba and Asahi Kasei Corporation also released a lithium-ion battery. Significant improvements in energy density were achieved in 1990s by replacing Yoshino's soft carbon anode first with hard carbon and later with graphite. In 1990, Jeff Dunn and two colleagues at Dalhousie University, Canada reported reversible intercalation of lithium ions into graphite in the presence of ethylene carbonate solvent, which is solid at room temperature and is mixed with other solvents to make a liquid. This represented the final innovation of the era that created the basic design of the modern lithium-ion batteries. In 2010, global lithium-ion battery production capacity was 20 gigawatt hours. By 2016, it was 28 gigawatt per hours, with 16.4 gigawatt per hours in China. Global production capacity was 767 gigawatts per hours in 2020, with China accounting for 75% production in 2021 is estimated by various sources to be between 200 and 600 gigawatts per hour, and predictions for 2023 range from 400 to 1,100 gigawatts per hour. In 2012, Goodenough, Richard Yazami, and Yoshino's received the 2012 IE3 Medal for Environmental and Safety Technologies for developing the lithium-ion battery. Goodenough, Whittingham, and Yoshino were awarded the 2019 Nobel Prize in Chemistry for the development of lithium-ion batteries, and Jeff Dunn received the ECS Battery Division Technology Award in 2011 and the Yeager Award from the International Battery Materials Association in 2016. In April 2025, Cottle unveiled its Shenxing Plus battery, the first lithium-ion phosphate battery claiming a range of over 1,000 kilometers, which is about 6 120 miles on a single charge. The company also stated the battery supports 4C ultra-fast charging, allowing for 600 kilometers of range to be added in 10 minutes, making a significant advance in making long-range fast charging LFP batteries viable for the mass market. And the chapter of design of cylindrical Panasonic 18650 lithium-ion cell before closing and lithium-ion battery monitoring electronic overcharge and deep discharge protection. Generally, the negative electrode of a conventional lithium-ion cell is made from graphite. The positive electrode is typically a metal oxide or phosphate. The electrolyte is a lithium salt in an organic solvent. The negative electrode, which is the anode, when the cell is discharging, and the positive electrode, which is the cathode, when discharging, are prevented from shorting by a separator, and the electrodes are connected to the power circuit through two pieces of metal called current collectors. The negative and positive electrodes swap their electrochemical roles in anode and cathode when the cell is charged. Despite this, in discussion of the battery design, the negative electrode of a rechargeable cell is often just called the anode and the positive electrode the cathode, and its fully lithiated state of Lic6. Graphite correlates to a theoretical capacity of 1,239 coulombs per gram, about 372 mAh per G. The positive electrode is generally one of three materials: a layer oxide such as lithium cobalt oxide, a polynion such as lithium iron phosphate, a spinel such as lithium manganese oxide. More experimental materials include graphene containing electrodes, although these remain far from commercially viable due to their high cost. Lithium reacts vigorously with water to form lithium hydroxide (LiOH) and hydrogen gas. Thus, a non aqueous electrolyte is typically used, and a sealed container rigidly excludes moisture from the battery pack. The non-aqueous electrolyte is typically a mixture of organic carbonates such as ethylene carbonate and polypropylene carbonate containing complexes of lithium ions. Ethylene carbonate is essential for making solid electrolyte interface on the carbonate anode, but since it is solid at room temperature, a liquid solvent such as propylene carbonate or diethylene carbonate is added. The electrolyte salt is almost always lithium hexafluorophosphate (LiPF6), which combines good ionic conductivity with chemical and electrochemical stability. The hexafluorophosphate anion is essential for passivating the aluminum current collector used for the positive electrode. A titanium tab is ultrasonically welded to the aluminum current collector. Other salts like lithium perchlorate, lithium tetrafluoroborate, and lithium bis are frequently used in research in tabless coin cells, but are not usable in large format cells, often because they are not compatible with the aluminum current collector. Copper with a spot welded nickel tab is used as the current collector at the negative electrode. Current collector design and surface treatments may take various forms: foil, mesh, foam, Deloyed, etched, wholly or selectively, and coated with various materials to improve electrical characteristics. And here there is a background for this three-dimensional lithium-ion battery. Prismatic batteries are widely used in automotive application and in battery energy storage systems. Three-dimensional models are interested to make accurate estimates of the impact of the current collectors and the position of the foil tabs on the current and potential distribution as well as the distribution of the heat generation in the cell. The model in this presentation is a full Newman model in three-dimensional, including the extra fourth dimension of the particle radius to describe lithium intercalation. In addition, the model also accounts for the conduction in the copper and aluminum foils as well as the heat generation due to ohmic losses and overvoltage losses in the foils, electrodes, and separator. Battery geometry model definition. Lithium-ion battery equipped with two jelly rolls, each JR or jelly rolls encompasses positive current collector foils, red and aluminum, positive electrode separator, negative electrodes, negative current collectors foils, blue and copper. Each foil has collector tabs that connect to the connector plates, and cell lid includes positive red and negative blue poles, each with corresponding connecting plates, top lid and insulating plates, and safety valves. Uh, about jelly rolls geometry model definition, a composite sheet is rolled according to the figure on the left. The composite sheet consists of individual layers of separator, a positive electrode collector foil, aluminum, a second positive electrode separator, a negative electrode collector foil, copper, and a second negative electrode. Notice that when the sheet is rolled, the inner first positive electrode doesn't face a counter electrode, which means that it cannot be utilized for charge and discharge. The same effect occurs for the last outer negative electrode in the jelly roll. The last layer doesn't face a counter electrode. The tabs in the collector foils are in electronic contact with the connector plates at their respective terminal poles, positive and negative poles. Model definition. The electrode and separator in the jelly rolls are modeled according to the so-called Newman model and included balance of ions and balance of current in the separator and in the pore electrolyte in the electrodes. Balance of current in the electronic conductors in the porous electrode and in the electrode collector foils fully coupled to the balance of current in the pore electrolyte in the porous electrodes through the electrochemical charge transfer reactions. Full electrodes kinetic expressions for the electrochemical charge transfer reactions, including the impact of local electronic and ionic potential as well as local composition. Balance of lithium and intercalation of lithium in the electrode particles, modeled using a fourth extra dimension. The heat balance includes heat sources from the electrochemical losses as well as the ohmic losses in the ionic and electronic conductors. Heat conduction in the electrodes and collector foils coupled to the connector plates and the positive and negative poles as well as to the surrounding insulating material and the external battery cap. Note that the above descriptions are already made in the lithium-ion battery interface. For example, you don't need to bother about defining the model equation. And here there is a COMSOL simulation implementation in COMSOL multiphysics. The electrochemistry and heat transfer problems are defined in the following ready-made interfaces: lithium-ion battery interface and heat transfer in solid interface. You can see that we have used two different physical modules: a lithium-ion battery and heat transfer in solid because there is a solid and we don't have the fluid flow or gas. All electrochemical properties are available in the battery design module, and the electrochemical heating feature couples the battery and heat transfer equations. The porous electrodes are modeled in three-dimensional using porous electrode theory, including particle intercalation and reaction kinetic. And you can see here the equation that there is here based on the porous electrode theory. The transport equations for intercalating species in this case is defined as a so-called extra dimension, which represents the radial coordinate of the particles. This means that the model includes the x, y, and z space dimensions plus a microscopic extra dimension representing the dimension along the radius of the particle, which is a fourth dimension. Note that you can also compute mechanical stress and strain in the particles due to the expansion and contraction during a charge-discharge cycle. The reaction kinetics for the electrochemical reactions are described using a built-in expression for the selected electron reactions, which yields the expression for the local current density. However, you can define any expression that depends on the local overvoltage and the local composition, including Butler-Volmer and TOEFL expression. You can also type in analytical functions of composition and overvoltage or use experimental lookup tables. Irreversible voltage losses occur due to the following phenomena. The first one is charge transport in the electrolyte Joule heating. The next one is charge transport in the solid conductor material Joule heating. And the third one is activation over potentials in the electrode reactions. And the fourth one is heat of mixing. In addition, reversible heat sources and sinks can appear due to the entropy changes in the electrode reactions. All of these terms are accounted for and added automatically to the heat transfer equations as local heat sources or heat sinks. The charge-discharge cycle is defined in the corresponding node. The cycle is repeated depending on the time interval defined in the time-dependent study step. For example, the study will accommodate the number of cycles that fit into the simulated time intervals. And you can see the plot, which is a cell voltage based on time. Time is in the x-axis, and in the y-axis you can see the fluctuating of voltage. And also in the voltage on the right side you can see the current based on ampere. So we want to check and compare and make a comparison between voltage and current here. So here is the discharge charge cycle, cell voltage versus current. The cell is discharged at 1C, about 70 ampere for 3075 seconds. It is then allowed to rest at open cell voltage until T is equal to 3580 seconds. From the 3580 seconds until T is equal to 6144 seconds, the cell is charged at about 17 ampere. Ohmic losses in the current collectors. One of the reasons for solving the three-dimensional problem is the structure of the current collector foils with the tabs at the upper part of the jelly roll. We can see some variations in electric potential along the height of the foil. The ohmic losses in the aluminum foil at a current of 1C are relatively small, is about 3.8 millivolt, both for discharge and charge. The potential distribution in the figures doesn't change to any visible degree with time, and not shown to during discharge nor during charge. This suggests that the current density distribution along the jelly roll is relatively uniform. If, for example, one end of the roll was discharged first, then the ohmic losses would change with time during discharge. Negative electron. ohmic loss in the current collector. The ohmic losses in the copper foil at a current of the 1C are relatively small, which is about 1.6 millivolt, both for discharge and charge. Since the conductivity of copper is higher than that of aluminum, the ohmic losses are substantially smaller for the negative electrode. Also, for the negative electrode, the current density distribution seems to be uniform along the length of the rod, since the ohmic losses don't change with time. Local current distribution. What we can see in these plots is that there are only small variations in local current density distribution along the length of the jelly roll, with the exception of the inner positive electrode and the outer negative electrode, which don't face counter electrodes. The lack of a current electrode also leads to edge effects at the end of the sheet layer of the roll, where the edge picks up a current from a larger part of the electrode that doesn't directly face a counter per electrode. The same effect is seen in the inner edge of the roll, not shown here. There are larger variation along the thickness of the electrode where the electrode is discharged close to the separator first. We can plot the current density distribution along different cut lines, such as the vertical cut lines shown in the plot to the right. Local current distribution. The local current distribution reveals how the electrodes are discharged at different positions. In this case, we would be interested to see the current density distribution along cut lines at 6 different locations. Close to the positive current collector's tabs, top part and bottom part of the jelly rolls, close to the negative current collector tabs, top and bottom, at the position further away from the collector tab along the jelly rolls at the end of the jelly roll, top and bottom. Local current distribution. During discharge, the negative electrode's local current density is anodic positive per definition, while the positive electrode's local current density is cathodic negative I local. The local current density along the thickness of the electrodes shows that at the beginning of the discharge, the negative electrode positive current has a substantially less uniform current density distribution than the positive electrode. This is because the electronic conductivity of the negative electrode is almost 30 times higher. This means that current transfer quickly from the poor electrolyte to the electronic conducting phase in the negative electrode, resulting in a high local current density close to the separator when the electrode is uniformly charged at the beginning of the discharge process. Local current distribution. The current density changes substantially at the end of the discharge process. At that stage, then the local stage of charge determines the local current density distribution. The parts of the electrodes that have not yet been discharged get a higher current density. At the negative electrode, positive local current, the local current density distribution becomes more uniform with higher values close to the current collector, where there is a higher state of charge. At the positive electrode, negative local current, the same effect is obtained, but even more pronounced, which is caused by a larger variation of a state of charge during the discharge process. The positions of the separator in green, negative current collector foil blue, and the positive current collector foil red are hinted in the first layer of the jelly roll. These positions are repeated across the thickness of the jelly roll but not shown here. Notice also that there is not reaction zero local current density in the most inner positive electrode and in the most outer negative electrode as expected. Local current distribution, electrodes position 1 charge. The situation is reverted when the cell is charged. The positive electrode is then the anode positive, and the negative electrode acts as a cathode or negative I local C blue. However, in this case, the plot is here. However, in this case, the effect of the local state of charge is more pronounced at beginning of the charge cycle. The local current density is higher close to the separator for both electrodes. However, after 2540 seconds of charge, the part of the positive electrode that are close to the separator gets a slightly lower local current density, suggesting that the charging process is moving inwards towards the center of the electrode. Electrodes position 1 and 2 local current distribution. The local current density distribution changed to a very small extent from top to bottom for both discharge and charge. This implies that the impact of the ohmic losses in the foil don't play a very important role along the height of the cell. The plots to the right show the local current density after charging at the top of the cell, position 1, and at the bottom of the cell, position 2. There is a difference in local current density distribution, but this difference is very small. The same conclusion holds for discharge. There is a small difference between top and bottom at these positions along the jelly rule and not plotted here. The local current density distribution at the position of the negative current collector taps, position 3, is also very similar to the one at the position of the positive current collector taps, position 1. This is disregarding of discharge or charge and of time. The same holds for the comparison between top position 3 and bottom position 4. The local current density distribution at position 4 is very similar to the position 3 at any time for charge and discharge. Conclusion. Local current distribution. If we also plot and the local current density distribution at position 6, we can conclude that there is only a small impact of the current collector force on the local current density distribution in the electrodes. This is expected from the plots of the total ohmic losses in the foils previously shown, which are 1.6 millivolt for the copper foil and 3.8 millivolt for the aluminum foil. The total losses in the cells are of the order of magnitude of the hundred of millivolt, which means that the foils losses are a relatively a small part, not negligible tool. This also implies that the utilization of the electrodes is fairly uniform along the length of the jelly roll. Notice the edge effect at the edge of the last composite sheets of the jelly roll. The last positive electrodes are almost not charged, not nor are they discharged. The current density is almost zero apart from the some bipolar effect. In addition, also the two last negative electrodes are discharged due to the fact that they can take up currents from the side, from the unpaired inner positive electrodes. Curved parts of the cell, a local current distribution. If we plot the local current density along a cut across the curved part of the cell, then we definitely see an effect along the thickness of the jelly roll. However, also this effect is relatively small. In addition, in reality, the external jelly roll layers would be stretched out a little more than the internal layers, leading to less active material per unit cell jelly roll length as the layers are stretched out. This is not taken into account in the model and would probably give an even more uniform local current density distribution if it was. A state of the charge. Since there are only a small variations in local current density distribution along the length of the jelly roll, we also expect a small variation in the state of charge lithiation in electrodes. This expectation is confirmed when plotting the state of charge in the jelly roll. Again, the exceptions are the inner and outer layers that lack counter electrodes and the edge of the roll where These edges pick up a current from the electrodes that don't directly face a counter electrode. The same effects are seen at the inner edge of the roll. The distribution of the state of charge reflects the local current density. There are some effects of curvature at the curved surfaces of the jelly roll, but these are relatively small. Temperature field. The temperature varies to a relatively small extent in the cell. The maximum temperature is obtained inside the jelly roll, more or less in the middle of the cell, which is expected since this is the position furthest away from the cooling surfaces. The temperature increases during discharge and charge. For example, it doesn't reach a steady state. Temperature across the jelly roll. The temperature along the cross sections of the jelly roll at the position reveal the importance of the metal foils in cooling the cell. At the position of the positive current collector tab, position 1, the positive current collector foil shows a local minimum in temperature while the negative foil shows a local maximum. The minimum is due to the cooling from the outside of the cell. The maximum is since it is the layer furthest away from the cooling tab. A similar effect but reverse is seen at the position of the negative foil. The components of the jelly roll layer tend to be cooled by the nearest foil which is closest to the tab. In all cases, the temperature is higher at the bottom of the cell compared to the top of the cell. This is explained by the fact that the cell is cooled to a larger extent by the highly conductive current collector foils conducting heat out of the cell than by the electrical insulator and the battery can at bottom of the cell. The temperature differences are small, tau less than 1 degrees of centigrade. External temperature. The external temperature varies due to high thermal conductivity of the metal parts relative to the low conductivity of the electrical insulators. The highest temperature is obtained at the bottom of the cell where the jelly roll is in close contact with the battery can. Possible future work. A very simplification of the model without the loss of any accuracy would be to treat only half of the cell, for example, only one of the jelly rolls, since there is a mirror plane along the middle of the cell. For three-dimensional models without thermal effects, it would be enough to model one winding, for example, from the negative to the positive tab. This would yield a good estimate of the impact of the ohmic losses in all windings. Since there is a pair of tabs for every winding, this would also confirm if a one-dimensional model can be used or not for the electrochemistry. An additional interesting analysis would be to model the same geometry with a one-dimensional description for the electrochemistry and three-dimensional description for the heat transfer, and then compare these with the results from the full model presented here. And the conclusion remarks: three-dimensional prismatic battery cell model. We can conclude that the three-dimensional effects for the model cell configuration are relatively small regarding local current density distribution and local state of charge. For most cases, we could probably treat the electrochemistry with a one-dimensional model to compare the local heat sources and then use a three-dimensional model for heat transfer only. However, the situation may change with different foil material and cell configuration. In addition, it may be useful to validate the accuracy of a one-dimensional model approximation using a full-dimensional model. Thank you so much for watching my tutorial video. Also, you can download this capsule simulation from my github.com/mahsa